Assalamualaikum everyone. Today our group will present on scaling with NoSQL from relational databases to distributed systems. I will start with the introduction explaining why relational databases were dominant for decades and how NoSQL emerged as a new solution. Now let's look at how traditional relational databases worked. For a long time, relational databases were the standard. They used normalization and ACID transactions to ensure data integrity, but there was a big problem. Scaling them was very difficult. If we needed more performance, we had to buy stronger servers and expensive licenses. This approach worked for small systems, but it was not practical for large global applications. So, relational databases struggled with horizontal scalability, meaning adding more servers to handle more users. Since relational databases struggled to scale, this led to the rise of NoSQL. In the 2000s, companies like Amazon, Google, and Facebook faced massive scalability challenges. They realized relational databases could not meet their needs, so they built their own custom data stores that focused on scalability and high availability. Later, open source NoSQL databases like Cassandra, MongoDB, Redis, and CouchDB became popular. It's important to note NoSQL is not a better SQL. Instead, it's a different approach designed to handle huge amounts of data by making trade offs. To understand these trade offs, we need to look at the CAP theorem. This will be explained by the next presenter of our group. Thank you for being with me.
The CAP theorem tells us that a distributed database cannot give all three things at the same time: consistency, availability, and partition tolerance. So, we must choose which two are more important for our system. This is why different NoSQL databases behave differently. Some focuses on availability, some focuses on consistency. In short, CAP explains the trade-off we must make when the system is spread across many servers. Now, eventual consistency. Eventual consistency means the system does not update all servers instantly. If one server gets updated first, the other server will become updated after some time. So, for a short moment, we may read older data, but eventually all servers will show the correct value. This method keeps the system fast and always available. Amazon's shopping cart is a common example. Availability is more important than strict real-time accuracy.
When multiple servers accept writes at the same time, conflicts happen. Different replicas may receive updates in different orders, leading to inconsistent versions of the same data. To handle this, distributed systems use different approaches. One is where last write wins. It resolves conflicts quickly, but the downside is that some updates might be overwritten and lost. A careful strategy is client-side merging, where the system combines different versions instead of discarding one. A typical example is a shopping cart. If two servers receive different cart updates, the client merges the items so that nothing is lost. Quorum consistency offers a structured way to balance latency and consistency across distributed replicas. The idea is simple. Before a read or write is confirmed, a majority of replicas must agree on the value. This ensures that the clients interact with the most recent stable version of the data, even if some nodes are temporarily unavailable. For writes, the operation succeeds only if enough nodes acknowledge it. For reads, the system consults a majority for accuracy. This approach significantly improves read after write guarantees, meaning that once the client writes something, subsequent reads will reliably return the updated value. In failure scenarios, quorum still works. Clients just need to reach a majority, not all nodes.
Okay, let's talk about MongoDB. MongoDB uses replica sets with one primary node and multiple secondary nodes. All writes go to the primary. If the primary fails, one secondary is automatically promoted through a election process. This reduces downtime, but because replica is asynchronous, recent data can be lost if the primary cache crashes before syncing. Then let's talk about Cassandra.
Cassandra uses a totally different design. It has a peer to peer architecture where all the nodes are equal and there is no master. Any node can handle client requests. Data is automatically distributed and replicate across the cluster. If one node fails, the system keeps working because their other nodes already hold copies. Then finally talk about the conclusion shows that NoSQL systems sacrifice strict consistency to achieve high scalability and availability. According to the CAP theorem, a system must make trades-off between consistency, availability, and the partition tolerance. So the choice depends on system needs. MongoDB for structured failover, Cassandra for massive and always on availability. Thank you.